Get rolling. Cool. So today we're going to be talking about, actually, first of all, can everyone hear me? Yes, no, maybe so?
Yeah.
Okay, great. Yeah, so today we're going to be continuing with anti-Markovnikov reactions and then finishing off with ozonolysis. Okay, so learning objectives. We'll first go over, review nucleophiles and electrophiles, as well as Markovnikov versus anti-Markovnikov, and what we exactly mean by that. And then we'll look at some reactions that convert alkenes to alcohols, as well as alkenes to ethers. And then we'll finish off with reactions that convert alkenes into aldehydes, ketones, and carboxylic acids, which is going to be super useful as you continue on through the course and think about synthesis. Okay. So the first thing that we're going to be thinking about is nucleophiles and electrophiles. And so if we remember from previous lectures, right, the nucleophile is going to be electron rich, and it wants to go towards these regions of lower electron density. So these atoms that have a delta plus or just a positive charge. And then the electrophile is going to be electron deficient, and it wants to go towards delta minus atoms or atoms that have a high amount of electron density. So it's also really important to not confuse electrophile with electron, right? So electrophiles are electron loving. So your reaction, and when you think about your curved arrows, it's always going to be nucleophile to electrophile, never the other way around. So let's kind of think about how to apply that and use that in an example. Right, so we're going to think about the reaction mechanism for this reaction here. And so can someone tell me kind of what would be the first step in drawing out the mechanism for the reaction? Anyone, any thoughts?
I guess determine what would be your nucleo and electrophile.
Yeah, exactly, spot on. So we would identify nucleophiles and electrophiles. And what would probably be the best nucleophile in this reaction? Anyone? So what do you think has the highest amount of electron density that it would be willing to share electrons? Anyone? Any thoughts? Even just like a gander at the answer.
Would it be the NH3?
Yeah, exactly. Right, because it's going to not have that positive charge and it has lone pairs to give. So we would draw our curved arrows like that. And then we would need to break this bond because oxygen needs to maintain a full octet, right? And so then our final product would look like this, NH4. And now if you do the counting, right, nitrogen usually prefers 5 valence electrons, but in this case, it's going to have 4. So it's going to have a +1 charge. And then we would just have water left over with 2 lone pairs. Cool. What questions are there on that problem? Okay, so let's do another one. This is one that you saw in your homework exam. All of them are kind of blurring together, but you've seen this problem before. And so once again, right, step 1 is going to be identifying our nucleophile and electrophile. And so what would probably be the best nucleophile and what would be the best electrophile?
Acetone would be the nucleophile.
Yeah, exactly. And where would I draw the curved arrow? Where should it go? Where should it end up? So if we think about it, right, this is H3O plus, which is just an acid. And what do acids do to things in solution?
They want to donate protons.
Yeah. So if they want to donate protons, a curved arrow should probably be like this. And although the plus charge is here, what we have to realize is that by making this oxygen even more electron deficient, right, oxygen is going to be way more electronegative than hydrogen, right? So by making it more electron deficient, it's just pulling even more electron density away from that hydrogen. So we would draw our curved arrows showing the start of the curved arrow coming from oxygen and ending at hydrogen, and we would break that bond. So oxygen still maintains a full octet. And so our final structure would look like this. And then we would have water. What questions are there on that? Okay, so that was our review of nucleophiles and electrophiles. Now let's think about Markovnikov versus anti-Markovnikov addition. So can someone tell me what the difference between the two is? Anyone? So what can you tell me about substitution patterns and regiochemistry when we think about those two? Okay, so when we think about Markovnikov, right, all that's saying is that our nucleophile is going to end up at the most substituted carbon when we're doing these alkene additions. And in the anti-Markovnikov, that's just saying that our nucleophile is going to end up at the least substituted position of our alkene. So when we're thinking about the Markovnikov addition using this alkene, right, our nucleophile would end up at the most substituted position, would be on this side of the original double bond. But then when we think about anti-Markovnikov, our nucleophile would end up at the least substituted side, which would be on this side of our double bond. So let's think about kind of the examples of Markovnikov addition that we've seen throughout the past couple of lectures. So the first is going to be this hydrohalogenation, which adds an HX to alkenes. And so the way that we've seen that done, right, we would have some alkene like this, and we'd add an HX. And then our final product would have our nucleophile at the most substituted position, and it would add our hydrogen right there. So that's hydrohalogenation. So this is essentially how you would add some kind of halogen along with a hydrogen onto an alkene. There's halohydrin formation, which is essentially just adding this alcohol onto an alkene in a Markovnikov fashion. So if you had something like this, right, you would have Br2, H2O, right, an excess. So your kind of final product. OH right there, and you would also have another thing of HBr. Right, so essentially in this reaction, you're going to have the OH being added on to the substituted position. And then we've kind of seen this in previous lectures with just a standard hydration reaction, which involves H3O plus and H2O. And it pretty much does the same thing as this, except of adding Br, we're just adding a hydrogen. And then the fourth one that we're going to see today, later on, is going to be this oxymercuration, alkoxymercuration. And this is a bit longer one, but we'll look into it later on in this lecture. Okay. Think about examples of the anti-Markovnikov additions. So there's really two big ones. So the first one is going to be this radical halogenation, which does the same exact thing as the hydrohalogenation. And so the way that that works is it's going to be adding an H and a Br, right, which is going to be synonymous with that HX. But it's doing it in an anti-Markovnikov fashion. And the way that we do that is by using peroxide, or OOR, and then we use it in the presence for the energy of a photon, because, you know, fun. And then OR, that's going to be the form that it's going to take in the reaction. And so your final product is going to be this. Right? But what you'll notice is that now we've added our Br onto the less substituted side of our alkene. And then hydroboration oxidation, you'll learn about that as well later on. So what questions are there so far?
I'm sorry, I just have a quick question. I'm not sure if it was just me, but you cut out when you were explaining the difference between, like, as to why it was being put on the least substituted carbon. Like, what is all that writing underneath the HBr?
Oh, yeah. So this is just going to have to do with the mechanism. I don't think you guys have seen the mechanism. You will see it later on in 3570. But long story short, it's just going to come down to the mechanism. But the important thing about the way the reaction is going to work is that it's using these peroxides, so ROOR, and then it's going to be in the presence of heat, which is here, or light. Does that answer your question?
Yes, thank you.
Okay, awesome. What other questions are there? Okay, so let's get into kind of our first reaction that we said we would talk about later, and that's going to be this reaction that converts alkenes into alcohols. And so it's going to be called oxymercuration reduction. Some places you might see it called oxymercuration demercuration reduction. Same exact thing and same mechanism. And so what this reaction is doing is it's going to add in, it's adding an alcohol in a Markovnikov addition manner. So what you see here, right? This would be the most substituted carbon. And so we're adding our nucleophile, this OH, onto the most substituted side. And so this reaction is going to be broken down into two steps. And so step one, let's kind of get into it. Don't worry if you can't like write everything as I'm writing it down. We will be posting the notes later on. Okay. But just kind of pay attention to the overall idea of the mechanism and feel free to ask questions as they come along. So this is going to take a little bit of space. So we'll start off with our alkene, right? And we're going to react it with this thing called mercury acetate, which is going to have two acetate groups, right? Which is this. And it's also going to have lone pairs on it. And this is going to be what's called a concerted addition. Okay, and so the first thing that we're going to do, right, is we're going to find what our nucleophile is going to be. And so in this case, you're going to have both the lone pairs on the mercury and part of the double bond acting as your nucleophiles. And the way that's going to work is you're going to do that, and then the double bond is going to break, and it's going to do that. Right? It's pretty similar to what you've seen with bromination reactions with like Br2. right? And so when you do that reaction, you also have to break a bond to the acetate because mercury won't, handle more than those two bonds. And so you're going to lose an OAC. And so your product is going to look like this, RC, R, and then you're going to form this kind of triangular intermediate, look similar to what we've seen with the bromination reactions. You'll get this, the CH2, and then you'll get OH, right? And so if you remember, we also were doing this reaction with water. So let's go back for a second, right? We're doing this reaction with mercury acetate and water. The reaction in this solvent, which is just, the solution the reaction is taking place in, and it's called THF mixed with H2O. So THF just stands for hydrofuran. And then the second step in the reaction takes place in sodium borohydride, this NaBH4, with sodium hydroxide, this NaOH. Okay, so let's go back, right? So we said we're going to be using water in this reaction. And so once you form this triangular intermediate, what you're going to have done next is water is going to come in and it's going to attack this carbon. Notice it's attacking on the side opposite of the mercury. You're going to break a bond here, and then it's going to go down this way. And what you're going to get next is this. So essentially, we've broken this bond to the mercury, and we've added in a water onto this carbon. So that'll look like this. Let me just erase parts of this so it doesn't get too cluttered. Okay. Okay, lone pair, plus charge. Okay, and then we're gonna have CH2 there, and it's still going to be attached to mercury and an acetate on one end, right? Because we only broke off this bond, not the other bond. Okay, and then from there, we're just gonna have that acetate that we lost here. We're gonna have it come back, and it's just gonna do a deprotonation reaction, right? Because our final product is going to have an alcohol, but right now we have this like weird three things happening here with like a plus charge. So to get rid of that, we'll just take away one of the OH, the H's on the OH, and then we'll be left with our alcohol. And so our final product of step one looks like this. CH2, HGOAC. Okay, so what questions are there so far? Okay, so now this is our final product of step one. Notice we still have this HGOAC, right? But our final product just has OH and H being added. So now our step two is going to be getting rid of that HGOAC. And for step two, it's a lot simpler than step one because you don't need to know the mechanism of step two. I think even in Loudon, it just says the mechanism isn't covered in the textbook, so that's great. Okay, so once you have this HGOAC, all you'll do is you react it with sodium borohydride, this NaBH4, and sodium hydroxide, this NaOH. And pretty much what the sodium borohydride is doing is it's going to act as a hydride source, which just means it's going to be giving H minuses. And these are going to be great for doing reduction reactions. And so what that means is it's going to be reducing this Hg, this mercury. And so once you've done that reaction, the final product is going to be RCROH, right? And now you're going to be replacing that mercury acetate with just a normal hydrogen. And so your byproducts are going to be NaBOH4, 4Hg, and it's going to be reduced all the way down to 0. It started off as mercury 2. And then our last byproduct is 4ACO. And don't worry too much about these byproducts. The main idea is you know how to get that product. Okay, now alkoxymercuration is going to be the exact same thing as oxymercuration reduction, except this time, instead of using water like we saw last time, we're just going to be using some kind of alcohol. And so all that means is we're using something that has a bunch of carbons and then an OH here. And when you used water, if you remember what happened there, right, all we did was we ended up taking away one of the hydrogens and we added in an OH. So with alkoxymercuration reduction, that should be OCH3. But anyways, so with alkoxymercuration reduction, all you're doing is you're going to be removing this hydrogen, and instead of adding an OH, right, you would be adding in an OCH3, right? That's what happens when you remove that H, and then your H is going to be added in right there. So now we've learned two ways to kind of take alkenes and do things with them, right? And the first way with oxymercuration, you can add in an alcohol. With alkoxymercuration, you can add in this ether functional group. Okay, so what questions are there? Okay, so let's go through one or two practice examples really quickly. So can someone tell me what the product of this reaction would be? And just to get you a hint, we'll just start off with this as part of the final product. Anyone? Any thoughts, ideas? So what do we know about this reaction? And specifically notice we're using H2O, which should tell us it's going to be oxymercuration reduction. What do we know about oxymercuration reduction? How does it add on our OH and our H? Any thoughts, ideas? Anyone?
So from the acetate groups, the mercury will form that triangular intermediate,
Yeah.
and then the water will attack one of the carbons to attach, and then the acetate group that's now free from the mercury will attack one of the hydrogens off of the water to take it off, so that way the water that's attached just becomes OH minus.
Yeah, exactly. And kind of putting all of that together, right? Our final product is just going to be this OH being added and this H being added, right? Because we used H2O in our reactions rather than some kind of alcohol. Okay, so let's look at another quick example. And so in this example, right, notice we're still using an H2O. And so what are you guys' thoughts on that? Right, when you react this kind of this, what would be kind of the final product? short is we're going to be adding in OH, right? We use H2O, and we're going to be adding it to the more substituted side, which would be this side of the alkene, right? Because it has 1, 2, 3 attachments. And so when we do that, we have our OH there, and we have our CH3 still here. And then the other side, we're just going to add our hydrogen. And so it would look like this. And one other thing to note about this is the stereochemistry. Note that the OH is always going to be on the opposite side as the hydrogen you're adding because of the way the triangular intermediate is working. So in this case, the OH is going to be on a wedge, and then the hydrogen is going to be on dashes. Okay, so I'm going to end it there for today. Yeah. And I'm going to pass it over to Ashley.
So let me just get to this slide that I'm going to start with. Okay. So I'm going to go over a reaction called Hydroboration Oxidation. So the main points for this reaction that I want you guys to remember are these points right here. Sorry. So first, if you look at, you have an alkene right here, right? And then you have 2 steps that are going to occur. First step involves BH3 and THF. And Corel kind of said what this means, but it looks like this. So THF looks like this. And then the second step is going to be H2O2 and NaOH. So this first step right here is why this hydroboration is in the title. So hydroboration, first step, oxidation, second step. So we start with this alkene right here, as you can see, and then we get this product right here. And the main thing I want you guys to focus on is, again, in this reaction, we're also working with just adding OH and H. But in this case, we're adding the H to the least substituted and the H to the most substituted and the OH to the least substituted. OH is our, if you want to think about it like nucleophile, right? Is in the least substituted. So this would be Anti-Markovnikov. So first, right, we're adding OH and H to the final product. And then this is Anti-Markovnikov addition because the H is added to the least substituted. And then I also want you guys to note that this reaction is going to be a syn addition, and then I'll explain later why it's a syn addition, and I'll kind of show you the mechanism for that. So essentially what that means, again, just to review, is that the H and the OH are going to be added to the same side of the double bond. So they're going to be either both wedges, both dashes, or both like lines like this. And lastly, there's going to be a concerted mechanism. So Corel kind of mentioned it as well. But essentially what this means is that there's going to be breaking of bonds, and bonds are going to be created, and that's going to occur at the same time. So with concerted mechanisms, because everything is occurring at the same time, you don't have a carbocation intermediate. So usually what that means, right, no carbocation intermediate, is that there's going to be no shifts, no methyl or hydrogen shifts. So in this reactions where you have concerted mechanisms, you don't have to worry about there being like a different product that you can create if you were to move something, because there's no carbocation, so you can't move anything. So this is a concerted mechanism. So let's now look at the mechanism itself. But so far, does anyone have any questions? Okay. So let's look at the first step. So again, kind of like Corel, he only drew the mechanism of the first step and not the second step. This is going to be the same for here. So let me go over the mechanism of the first step. We start with an alkene right here. And then we have, so if you guys, let's go back. You guys remember the first step involves BH3 and THF. So BH3 is the one that is going to react, and THF is kind of like the solution, or this can also be ether. Notice how I drew the bond for one of the H's and not the other one. That's because we're going to focus on how this H reacts with the alkene. So let's look at this drawing over here. So this brackets right here and this sign right here is the signal for a transition state. So whenever we draw a transition state, we kind of denote it like this. So this is a transition state, and a transition state is like a model of what is predicted to occur in order to get to like a product, right? So this, you cannot isolate this. So that's how it's different from an intermediate. You can isolate intermediates, but you cannot isolate transition states. So let's focus on what is occurring here. So essentially what is occurring is that this is a concerted transition state step. So this two things are occurring at the same time. So again, that's why there's no carbocation intermediates and no methyl or hydrogen shifts. So we don't have to worry about that. So we have this bond from the double bond, right? Those electrons are going to go to B. So now we're going to create a bond between the carbon and bromine. And then this bond between bromine and the hydrogen is going to break, and those electrons are going to go to C. So we're going to be forming a bond between C and H. So, right, so we have broken this bond and one of the double bonds and have formed a bond between C and H and B and C right here. And also, just to note, so you guys remember, whenever you have kind of like a carbon like this is sp2 plus p, right? So it's kind of planar. So this one's also sp2 plus p. So it's planar, right? So this BH3 is adding from one side of that plane molecule. So it's going to either add from the top or the bottom. So you're going to be able to have two different products. But for right now, let's not focus on that. So this is just saying what I just mentioned right now. This is a concerted transition state where you're creating CH bond and BC bond. So this bond right here and this bond right here are occurring at the same time. And this is syn addition. So that step is going to occur 3 times. But let's focus first on, so this is going to occur, you're going to get this product right here. So notice how this is the CH bond that we just created and the BC bond we just created. And this B still has 2 H's, so that's why we're drawing 2 H's here. So then this transition state, or this is going to occur again, as you can see from right here. So we're going to again create another bond between C and B. As this bond breaks, right, with these 2 electrons, we're going to form a bond here. This bond is going to break. Those electrons are going to form a bond between C and H. So now we have, so as you can see here, as parentheses denoted in 2, because this is going to create another substituent that looks like this. So there's 2 substituents that look like this. So we can just denote it with parentheses 2. And then that B is still attached to an H. And then again, the same thing is going to occur because this is going to occur 3 times. So we're going to form, so this double bond right here is going to form or move to form a bond between C and B at the same time as this bond breaks and forms a bond between H and C. So at the end, we're going to have something that looks like this right here. So again, this just denotes that there's 3 of the same substituents. So we're just going to have 3 substituents that look like this. Does anyone have any questions so far on this? Okay. So that one, like if they were to ask you to draw that, that would be a lot of work. So sometimes it depends on the professor, right? What they tell you, what they want. You can just draw it once, kind of just show it like this, or you can draw it once, right? And then just do 2 times and then to your final product of this. So that was the first step, right? So this is the mechanism for the first step. This is the product of our first step right here. So now we take that product and then look at the second step. So this is the product of the first step. Again, for the second step, you don't have to know the mechanism. All you have to know is that the second step involves H2O2 and NaOH. Essentially, what's going to happen is that, so let me just draw with this. I'm just going to denote the substituents as R's. So B looks like this right now. It has 3 different things attached to it. So essentially what's going to happen is that for each R is going to become attached to an OH like this. So that's why we have 3, that instead of this being attached to a B right here, it's attached to an OH. So we have 3 of those same products. And then this is just the side product. And this side product comes from B becomes attached. So B becomes attached to 4 OHs. And this is denoted as a negative, but it has a Na. So Na has a plus sign like this. So this is how we got this product. Is there any questions so far? Also notice how, so this OH right here was added to the least substituted one. So that's why it's Anti-Markovnikov. Okay. Let's do a practice question. So here we don't have to draw the mechanism, we just want the products. Does anyone want to tell me, if you guys remember, if this is Markovnikov or Anti-Markovnikov? Does the OH go to the most substituted or least substituted?
It's Anti-Markovnikov.
Yeah, so this one's Anti-Markovnikov. So let's just write down the important things for these reactions before we go into the actually drawing the product. So what else is important? So we also talked about whether it was syn or anti-addition. So like if it added from the same plane, you know, like if both of them are wedges or both dashes, or one is up dash or what is a wedge. So what do you think it is? Is it syn addition or anti-addition? And just to help you guys out, again, this is sp2 plus b, so it's planar, right? And then this is a concerted mechanism. So is it syn addition or anti-addition?
Syn.
Yeah, it's syn addition. And then we also mentioned how the overall thing we're adding to this reaction is an H and an OH. So the product is going to have an H and an OH at the end. So because we're having, you know, it's Anti-Markovnikov, so we know that we're going to have an H added to this carbon right here, and then the OH is going to add over here. But then we also know it's syn addition, and it can occur from the top or the bottom. So then we're able to have 2 different products because it's able to add to the top or the bottom. So then it's going to look, so this is the products right here. So this is when it's added from the bottom, and this is when it's added from the top. Does that make sense? Does anyone have any questions? So again, this is our dashes, both dashes or both wedges, because they're syn addition, same side, and Anti-Markovnikov, which is why OH is added to the least substituted carbon. And this is just for you guys to look at, but if, let me just go over real quickly. So again, this double bond, there's a, it goes to this B, so it forms a bond between this carbon here. This bond breaks, this forms a bond between this carbon and this H right here. So we have something that looks like this. And again, we said it's in addition, so they're both on the same side. So it can come from the top or the bottom as well. So we have 2. These are both wedges or both dashes, right? And then this is from the first step, right, where BH2 adds. And then from the second step, that's where the OH comes in. And OH just replaces BH2. So you can see this becomes this, and this becomes this. And as you may have noticed, when OH adds, there's no inversion of stereochemistry. So there's retention of stereochemistry, right? Because the stereochemistry stays the same. So retention of stereochemistry for the second step when OH is replaced. Sorry, BH2 is replaced by OH. Does that make sense? Is there any questions on this? Okay, let's do another practice question. So we just went over 3 things that are important for this reaction. So does anyone want to tell me what those 3 things are? The first one was Anti-Markovnikov or Markovnikov. Which one is it? So it's still the same reaction. We're still working with hydroboration oxidation. So is this Anti-Markovnikov or Markovnikov addition? You can also chat if you don't want to speak out. Yeah, someone said anti, you're correct. So this is anti-Markovnikov, anti-M. So what else is important for this equation? Yes, in addition. And then what else? What is added to the final product? In terms of, you replace a double bond and then what is added? Yeah, H and OH. So then, does someone want to guess how the final product is going to look like? So where is we said it's anti-Markovnikov, so where is, so this carbon number 1, carbon number 2, where is that OH being added to? Carbon number 1 or carbon number 2? Yeah,
The
carbon
H will
number
be added to, oh, sorry.
Yeah, go for it.
I was gonna say the H will be added
Yeah.
to carbon 1 and then the OH to carbon 2.
Yeah, exactly, you're correct. So I'm not gonna waste my time drawing that, so I actually drew it here. So you have your H in carbon number 1 and your OH in carbon number 2. And notice how, I said that, double bond, they're sp2, so it's planar, so you could add from the top. So if you add it from the top, it looks like this. And notice how it pushes these two down, but you still have, so CH3 right here, this methyl, and H are still on the same side. So this CH3 and H are both dashes. And then these two at the front are both wedges together. So they stay in the same side. The only thing that's happening is that they're being pushed down and you're adding this syn. And then this is when you add it from the bottom. And because the only difference of how this is added, right, they're added to the same carbons, but the only difference is that one is added from the top and the bottom. So that changes kind of inverts the stereochemistry. So they're enantiomers. Does that make sense? Does anyone have any questions? Okay. Move on. So the last reaction we're going to talk about is ozonolysis. So ozonolysis is essentially when you have an alkene and it reacts with ozone. So ozone is this molecule right here, O3. So you can also see it right here. And this reaction causes the cleavage of the alkene. This alkene right here splits the bond in two and forms two products, as you can see here. So there's two different scenarios, right? So this reaction has two steps, one being reacting with ozone and the second one reacting with either DMS or H2O2. So whether it depends on what the second step is, and let me rephrase that. So whatever the second step is, that's going to change your products. So if you have DMS as your second step right here, then all the H's in the aldehydes are going to be preserved. So let's look at this molecule right here, this alkene. What is happening is that this bond is being cleaved. And so this carbon right here is double bonded to this carbon. But instead, what's going to happen is that this double bond is going to be cleaved. And this carbon is going to form a double bond with the O instead. So you can see this carbon number 1 right here. This carbon is double bonded with an O. The same thing is going to happen to carbon number 2. So this carbon number 2 is double bonded to this carbon number 1. But instead, what's going to happen when it reacts is that this bond is going to be cleaved and it's going to form a double bond with an oxygen right here. So you can see the oxygen. So that's carbon number 1, carbon number 2 right here. And they have the same it's attached to the same thing, so that doesn't change, right? So if you notice, this is a ketone. And this is an aldehyde if the H, so let me just draw that. And I'll explain why I have an X right there in a moment. So this is an aldehyde. Oh no, okay. Undo, okay. So I said if it reacts with number 1, so DMS, the aldehydes are preserved, or the hydrogens in the aldehydes are preserved. Sorry, I can't speak today. But so if it reacts with step 2 being DMS, I keep saying DMS, so I'm sorry, it's DMS. It's just going to stay as an aldehyde, so it's going to stay the same. But if it's step 2, where it's H2O2, what's going to happen is that instead of this being an H, it's going to be an alcohol. So it's going to become a carboxylic acid. So essentially what happens is that it oxidizes any aldehydes to carboxylic acids if there is an H2O2. Does that make sense? Are there any questions? Okay. So let's look at the 2 steps or 2 scenarios in detail. So scenario number 1, we have DMS right here. So DMS, you can write it as you could see right here, it's just S and then CH3 and then 2 CH3. So it can also be written as S methyl, because this is a methyl 2. So they all mean the same thing. So this is the first step, and this first step, again, when there's DMS, there's retention of aldehydes. So what happens again is that the double bond is cleaved, and instead of being double bonded to another carbon, each carbon from the double bond is going to be double bonded to an oxygen. So instead, it's going to look like this right here. So you have a ketone here. Again, it's still double bonded to the 2 R's. And then this over here, I'm missing a carbon right there. So now it's double bonded still to 2 H's. Sorry, not double bonded to 2 H's. Bonded to 2 H's, double bonded to an oxygen. So this is an aldehyde, right? And it stays the same. Does anyone have any questions? Okay. Let's look at the second scenario. Right here. In the second scenario, we have H2O and H2O2. So again, this is peroxide. So in this case, whenever we have this one, and this should be step 2, what happens is that aldehydes turn into carboxylic acid. So it's going to be the same products as the other one, except just one minor change. So we still have the ketone, nothing, so this right here doesn't affect the R's, or again, R's means the rest of the molecule. But it does affect this one, where one of the H's so we go back right here. You remember that this one right here had 2 H's attached to it, but now one of the H's is going to be replaced by OH, and this is going to be a carboxylic acid. Does that make sense to everyone? Okay, so for this one, you guys don't really have to know the mechanism, but I thought I would include it just so you guys can see that it's very complicated. You guys don't have to know this for 3570, but you do have to know it for 3580. We're not going to focus on it this summer because, as you can see, it's very complicated. But yeah, if it's here, if you guys want to look at it, but I wouldn't worry too much about it for now. So let's do some practice. Let me just zoom in. Number 1. Does anyone want to attempt to do this question right here? Again, DMS, the hydrogens are not replaced by OH, so aldehydes are retained. So what do you guys think would be? So let me just start it off for you guys, right? So we have a C double bonded to an O, and then what is bounded to this carbon? You can start from either side. Or if you have a question, you can also ask. Yeah, so people are saying R groups. More specifically, it's going to be bonded to this one, right? Because essentially what you do is that you split this bond in two. So these two groups stay together, and these two groups stay together. So it could be, so let me just erase the C because it's easier to draw it just like this. And then there would be the H that right there that's not drawn. And then your other one would be CH2, right? Or you can just draw it like this. Does that make sense to everyone? Okay. Let's do another problem. Let me erase this. So let's do problem number 2. Does anyone want to give it a try? This one's a little bit more complicated, right? It's a ring. What do you guys think that's gonna happen? So so here are our steps. Does this retain aldehydes or okay? Does it retain aldehydes or does it turn into carboxylic acids? So this is DMS.
It would retain them.
Yeah, it's gonna retain them. So I know it's hard to explain, so that's why I'm just gonna give the answers because it's hard to explain by words how it seems, but essentially what this looks like, right? What is gonna happen is that you're gonna cleave this double bond right here, but these two carbons are still attached to this ring. So they're gonna stay together through this ring, but they're no longer gonna be double bonded to each other and stop double bonded to an O. So you can see this side is this side right here. You still have the same things attached to that carbon. So this is CH3, CH3, and then the rest of the molecule. And then here, this aldehyde right here was retained, like this H right here will stay the same. It didn't turn to an OH. So the aldehyde was retained because it's DMS. And if you were to count the carbons, 1, 2, 3, 4, 5, 6, they should be the same. 1, 2, 3, 4, 5, 6. So okay, so somebody asked, how do you know the aldehyde was retained? So if it's DMS, it's always going to be retained. If you have H2O2, H2O2 means, so H2O2 in your second step instead of this, then it's going to be H2O2 is going to replace aldehyde with carboxylic acid. Did that answer your question? Okay. So, unfortunately, I already shown you guys this number 3 right here. Just to go over real quick, this is an example when you have H2O2 and H2O at step 2. So this means that the aldehydes are going to be converted to carboxylic acids. So again, we're splitting this bond in two. So this part, these two substituents should stay in the same carbon because they're attached to the same carbon, right? So this part right here, and then that carbon, instead of being double bonded to another carbon, is double bonded to an oxygen. And the same here, except here, there's a hydrogen right here, right? So you can see that this hydrogen was replaced by an OH, and now this is carboxylic acid. And this is a ketone. Does that make sense? Is there any questions? Okay, so that was it for today. If there's any questions, me or Cornell are going to be here. Sorry, Cora are going to be here for a few minutes, but that's it.
Thank you.